Chapter 4, Linux File System Management, Part 2. So we left off our previous lecture on the topic of linking files and the whole idea behind linked files. Well, we can't make any sense out of what a linked file is until we understand how linking happens and how the operating system actually stores data on its disk. So let's take a look at this. So we're going to want to take a look. It stores it on a hard disk, right? So let's go ahead and draw a disk in. So I got this going on. Here's a disk. All right. It's a little misshapen, but that's at the top. We're looking down at a platter, at a hard disk platter there. Well, disks store their data in concentric rings, right? Kind of like so. There we go. Wow. Looks more like a peanut, but it's a disk, and it stores data in these concentric rings called tracks. And then the tracks, and it is a track, right? Like a racetrack. One continuous line all the way around. And then the disk is subdivided like this. There we go. And these smaller containers, from a physical perspective, are called sectors. Well, the operating system, the file system, sees this as blocks, right? And these blocks become the containers by which the file system stores the actual data in. So, how does it keep track of all this? How does it even know what's going on here? Well, the file system can be actually broken out into three primary pieces, right? For one, you've got something called a superblock. And in reality, you have several of them. But the superblock is what goes in and tells the file system about the disk structure, right? What blocks are in there. It's like the master directory, you will, of the entire operation. And then we make use of something, and actually let me get rid of that. A little eraser here, there we go. Gone. Then we have something called an inode table. Let's take a look at that. An inode table is really a listing of inodes to where they live on the disk. So you're probably saying, what's an inode, right? An inode is not the data on the disk. An inode is really a piece of metadata that goes in and it describes everything about, let's say, that file that we saved off. I saved off file 1, right? Let's put that down here. There, file 1. I touch file 1 on my files on my command line, and I hit enter, and I see file 1 appeared. Well, what happened was, the name file 1 itself, what I actually type in, what I actually see in the file system, is nothing but a label. That's all that it is. It's actually called a hard link. And I'm not limited to my number of links. More on that here in a minute. But when the characters file 1, nothing but a label. Inside my file system, at the time that it was formatted, back when I did when I formatted that disk or I formatted that partition, it created a finite number of inodes. Right? And there's tens of thousands of them, hundreds of thousands of them. It's based on the size of your disk and all that. But let's just say, for simplicity's sake, it created 100 inodes. And that, again, that's way tiny. We're talking hundreds of thousands of inodes, but we're going to put it in little bite-sized numbers. When I formatted my disk, it created 100 inodes. Well, an inode is really just an empty container that describes data on a disk. So it has things in there like file permissions, ownership information, access time, last modified time, and probably most importantly, directions to where the actual data is out here on the disk. The one thing the inode does not have, the file name. That's down here. That's this label. The reason that my file name is a link when I touch file 1 and created it, what that command actually did is it went and grabbed an available inode, right? So if I started with 100, I touched file 1, now I have 99 left, because once it's used, at least until you delete the file. And then this link right here points to that inode, right? So my data on the disk, my file, is actually comprised of three things: the label, the inode, and the block on the disk where it actually lives. So data is actually here. This is a container that tells me about that data, and here's the label to my data, and really just a pointer to it. Now that's actually a poor term because we have something called a pointer, which is a bit different, but we'll get to that. So what happens when I do another file? If I do file 2, same thing. It's going to go out and grab an available inode. So now I'm down to 98 free inodes, populate it full of information about that file, and point to where that data actually lives out on the disk, and so on and so forth. What do you think happens if I run out of inodes? Right? Think about that for a minute. What actually happens is I get a disk full error. Well, that can totally happen. In our little example here, let's just say this is a 1 gigabyte disk, right? We're going small for mental stress purposes. And I have 100 inodes in that file system. Well, if I save off 100 1 meg files, right, each one of those is going to use an inode, and the actual space on the disk that I've consumed is really, let's see, 100 times 1 meg, 100 meg. But my actual available disk space is 1 gigabyte. But if I'm out of inodes, I have nothing else to attach my labels to, nothing else to attach my links to. So the file system sees that space as being full, and it won't let me do anything else until I clear up some inodes. How do I clear inodes? Well, remember that rm command we talked about? So let's say I do an rm file 1. Enter. What that command really does is it goes out and removes the link. Just like that. The inode still has the metadata inside of it, but that file is not recoverable to me anymore, right? The data still lives on the disk, but I can't get to it. Now, I could forensically recover it. I mean, that's what that whole data recovery thing is. So if you remove a file, and that's why just deleting files off a disk doesn't remove the data from it, right? So if you got a hard disk with a bunch of real secret information on it, your personal information, your bank account information, and it's all in an Excel document, and you're like, rm myfile.xls, enter, take the disk, throw it in the trash can, all you've done is remove the link to the inode. Right? For all practical purposes, that file has been deleted, but really the inode is still there with that information in it, and the actual data is still on a block on the disk. So how does this free up an inode? Well, with no link on it, now the inode is considered free to grab by the next file. So when I do touch file 2, it has a perfectly good chance of grabbing that same inode, because inodes are numbered, right? This is inode number 10. Maybe I'll pull inode 10 again, and then it'll refer to some different data on the disk when I write file 2. The actual ones and zeros that represent my file continue to live on the disk until they're eventually overwritten, right? Because an orphaned inode just means now there's nothing protecting this block. It'll just, in time, it'll get overwritten. Okay. Let's take a closer look at our links. Let's get rid of that. I need a fatter eraser for this. You know what? There we go. Okay. Let's put our file back. There we go. A link that points directly to an inode, like this one does, file 1, is what's called a hard link. Right? By definition, hard links are labels that point directly to an inode, which in turn points to data on disk. I can have more than one hard link. I could have this right here. This case, this actual data, which is out here on disk, this file, right, there it is, has two hard links. So it appears, when I do a directory listing, as two files, file 1, file 2. But both hard links point to the same inode, which in turn points to the same data on disk. This is the same file. Right? If I change something, if I open up file 1 in Vim, change it, hit save, that change is going to show under file 2 because it's the same actual bit of data. And I'm not limited to 2. I can have many hard links as I want. Let's say I remove rm file 1 again. All right, gone. Get out of there. There, that link is gone. Deleted. Is my data still accessible? Yes, because I still have a hard link pointing to it. Right? As long as I have at least one hard link pointing to an inode, then my data is accessible. If I delete file 2, no, my data is no longer accessible whatsoever. Right? An orphaned inode pointing to some data, ones and zeros on the disk, for all practical purposes, is inaccessible to us. Right? I'm going to erase that a little bit more. So I can totally have more than one hard link. And I might want to. Right? We do this quite a bit, especially in scripting. We want to talk to the same file, but we want to refer to it using different labels. Okay. Let's put file 1 back. There we go. My other kind of link is called a soft link or a symbolic link. This is where the label doesn't point to the inode. All right, so let me get rid of this. It doesn't point to the inode, it points to another link. I created another label, but instead of pointing it up to the actual inode, inode 10, I'm pointing it to the hard link that points to inode 10. What does this do for me? Well, if I do a directory listing and look at it, I'm going to see two files, file 1, file 2. Same thing, you're still ultimately pointing to the same ones and zeros on disk. So I crack open file 1 in Vim, make some changes, hit save, cat file 2, I'm going to see those changes, right? Same data. Here's the difference. Whereas I could have, as long as I had one hard link, and I had multiple hard links, as long as I had only one pointing to my inode, I could access the data. This soft link doesn't point to an inode, it points to this file. So if I do an rm file 2, right, it removes this. Soft link is gone. Data still accessible? Yep, because I have a hard link right here. If I rm file 1, get rid of that, get rid of all that. There we go. Now is my data still accessible? No. I have an orphan label. It's pointing to nothing. I blew away its target. File 1 was the last hard link pointing to this inode. So I can have orphan symlinks sitting out there. So we need to think about that when you're creating your different links. What's the difference? Why would I use one over the other? Well, there's one really important rule. When we format a disk, we use this term quite a bit. I'm going to format a disk. What we're really doing is formatting a disk partition, right? Or specifically a storage volume, but we can think of it right now in terms of a disk partition. And every disk has at least one partition, right? It may have only a single partition in there, partition 1 that takes up the entire disk, but I've got at least one. Well, very commonly, I have more than one disk in my system or more than one partition. Right? I got another disk over here, and they're mounted to my file hierarchy in different places. Hard links can only be used within their same file system. Right? So if I formatted this disk right here, this is one giant partition, and I formatted it using ext3, and that generated a finite number of inodes and my inode table and a super block and all that stuff. And then I took this partition over here, let's say this guy, and I formatted it with ext3. That's a separate file system. It has its own inode table, its own super block, all of that. Now I can mount either of these partitions of these file systems into my overall directory hierarchy through something called a mount point. We'll be spending more time on that later. But I can totally do that. And when I'm inside my directory structure, it's invisible to me. I can't really see it. Hard links, however, can only be used within their own file system. And that kind of makes total sense, right? For a hard link to work, it must see the inode. Well, the inode's not visible outside of the file system. So for this one, I can put file 1, file 2, whatever, and have all these hard links pointing in here. But from this file system, I can't see these inodes. I can see these labels because they're in the directory hierarchy. So what I would do then, if I wanted to link to data on this file system, is I would have to do a soft link. And point to what I can see out there, which is the label. Now I can reference across file systems, and that's the whole point. That's the whole reason why we do this. So let's get down and figure out how we actually do this. All right, so let's go back to our terminal window. And here we are. So here I am sitting back in Bob's home directory. Let's do an ls. Well, and let's start again with file 1. So I'm going to touch file 1. And there it is showing up in my file structure. What did I actually do though? I created a label called file 1. We're looking at a label right here. That's all that it is. That in turn points to an inode, which in turn points to a space on the disk. So let's say I want to make a hard link. We use the ln command, right? Here's a perfect chance to practice our man pages again. If I man ln, ooh, look at this. makes links between files. And look at my synopsis, my overall structure. Target, link name. Okay. So, ln, my target, which is file 1, and my link name. Look at that. Now I have a file 2. These file 1, file 2 points to the exact same data. If I go in here and make some changes to it, right, I'm going to insert, this is a great text file, right, I'm going to do that, right quick, cat file 1, there's my contents. Look what happens when I cat file 2. The exact same contents. I'm looking at the same spot on disk. If I rm file 1, all I did is I blew away file 1's label. And if I cat file 2, my data is still there. Nothing but labels pointing to inodes. What about a soft link? Well, I can totally make one of those. Right? So let's go ahead and look at this. And let's create something called file 4. But that's going to be a symbolic link, a soft link to file 2. I invoke a soft link with the -s switch, ln-s. My target things look a little different here. There's file 4. Now notice the color, right? The bash shell, if you have color turned on, will give that a different color. That's like a teal or some kind of light green looking color, aqua, whatever. So that tells me right there it's a symlink. But look what happens when I do a long directory listing. There's my hard link right there. And look at my symlink, right? File 4, and it's pointing to file 2. That's how I know that's a symlink. Also, over here in my permissions, which we'll talk about next lecture, that gives me an L in my first character, which means soft link. If I do a cat on file 4, there's my text file, right? If I blow away file 2, look what happens to file 4. It turned all kinds of angry colors, red and black, right? It's orphaned. Yeah, file 4? What? There's no such file. Its target, it's pointing to, its label is pointing to, its hard link is pointing to, is gone. Look at that. That's their version of what I drew. I think mine's way better. And that brings us to the end of part 2. When we come back, we're going to take this information and we're going to start diving down into permissions, specifically file and directory permissions, data protection. It's the whole reason we have multi-user operating systems. I'll see you in the next lecture.